Hey, Physics 100 students, this is Dr. Kato. The last topic I just want to spend a little bit of time on is talking about how internal combustion engines, which is the engines in our cars and trucks, as well as a little bit of time on how jet engines work, okay, and how the overall energy that goes into your car gets distributed and used up while you drive down the road. Where does it all wind up? So there's a great diagram in your book related to that. So all of the images that I'm going to show you now, if you want to look at them on your own, you should. They are in the Chapter 5 images from the new textbook, which is you guys have in Moodle, loaded in Moodle. Okay, so this is figure 5.10. It's a cutaway diagram of a 4-cylinder engine. So what you can see, interestingly enough, is these are the 4 cylinders. 2 of them are maxed out down at the bottom, the 2 in the middle, and these 2 are kind of in their upward position. So in this particular 4-stroke engine, what you see is that at any given time, 2 of them are up and 2 of them are down. Now, typical amounts of times that these things cycle through the 4 cycles that I'm going to go on is cars probably idle at around 1,000 revolutions per minute, which is called RPMs, right? And probably go up, and they redline. You don't want to press the gas when you're in neutral or in park higher than something like 7,000, 8,000 RPMs. It becomes dangerous for the engine. So usually we're driving around at like maybe 3,000 or 4,000 revolutions per minute. Okay. Again, much faster than your eyes could ever pick up. You could not watch the cylinders go up and down with the naked eye, but all of the mechanics is worked out and has been worked out for 70 or 80 years and make this process work very well. Okay, so let's talk about very quickly, just talk about the 4 strokes. So if this cylinder number 1 over here is kind of up towards the top, so it's just about, let me start out with these 2 down ones, okay? So these 2 down here are just on their way, or just finishing up the intake stroke. So what happens with the intake stroke is that when you get to the bottom here, air, a valve over here opens up, okay, intake valve opens up, the exhaust valve closes up, and air gets rushed into this cylinder because it's under low pressure because it just evacuated itself by pulling itself down to the bottom. And fuel from the fuel injector system gets introduced into the chamber. So that's the intake portion, okay? So right after it reaches the bottom, air and fuel fill up the chamber, okay? Then it rushes up into what this cylinder is doing, closes up, so it would be all the way up here, and all of that hot gas from the air and the fuel is pressurized. And at that point, right after the compression, the spark plug would go off. A small explosion would occur in this cylinder, just about to explode in this cylinder, and then force the cylinder back down. So only one of the 4 actually provides the power. This stroke right here, where the explosion takes place, provides all the power, and then the other 3 are just maintenance that go around in a circle. Okay, so after the power stroke occurs and it forces this piston back down to the bottom, the next thing that has to happen is the intake valve is closed off and the exhaust valve would be opened up. And this time, when it comes back up again, instead of compressing hot air, it pushes the dirty exhaust that just got burnt out, and then in this closed up position, starts the intake cycle all over again. So those 4 cycles happen over and over again, all 4 of them, more than 1,000 times every minute in each one of these cylinders. The reason why they're offset is look at the way the crankshaft are. Even these 2 that are down here, they are in sort of slightly different positions. So you want, at any instant of time, one of them to be pushing down while one of them is picking up. Almost like when you're pedaling your bike, you provide most of the power on the downstroke. So you're pushing down, and then the other foot is kind of resting on the way down. So you're only getting power on one half of the stroke that you go around. Okay? This is a great diagram, right? I'd love to ask you a question where you had this diagram open, right? And I think I'm going to. So this is something that you want to keep open. So of all of the energy that comes in the chemical energy that's locked up in the gasoline, and how could we figure out what that is? Well, we could do our delta H calculation for one of the gasoline components, which is isooctane, and from that we get a pretty good estimate of the amount of energy that's actually contained in the fuel, how much you could extract if, this is a big if 100% of that energy that you get that is released when you form carbon dioxide and water vapor from fuel and oxygen could be converted into mechanical energy. And that's a big if, because as you're going to see in this process, we're not going to get anywhere near 100% out. So this is a gallon of gasoline sitting over here, sitting in your tank, ready to burn. Okay? Well, how much of it's going to come out the other side? Well, you're going to see the total amount that gets to the wheels is only going to be 15%. So 85% of it is going to be wasted on the way, which is unbelievable. So your car is very energy inefficient. Okay, so the first thing that happens inside your car, 18%, about 20% of the energy that comes from those explosions of the gasoline gets converted into mechanical energy that's turning the crankshaft here down at the bottom. So 100% of the fuel energy in the gasoline, when this process goes, only 20% of it gets to actually moving this crankshaft up and down. So the engine itself is 20% efficient. Well, where are the losses then? Where's the other 80%? Well, 62% of it are thermodynamic losses, are lost by heat that just gets lost to the engine components and to the exhaust that comes out hot. So this is waste heat from the radiator and the exhaust gases. Where's the other 18% lost, right? So 62 and 18. So the other 18% is frictional losses within the engine, right? All of these parts are rubbing against each other. They're not 100% efficient. The better you make the car, the more efficient this part can be. So this can be dropped down to much less. But a typical car today has 18% friction inside the engine. So 62. So this gets you to 80 right here. Okay? All right. So the 20% that makes it out of the engine, 2% of it is lost to accessories. So what are those accessories? Your air conditioning, your radio, and your alternator to run the lights and all of those systems that keep your battery charged. Okay, that means 18% of it makes it to the transmission. The transmission loses a little bit. It loses 3%. That means only 15% of it gets to the wheels. See if I fix that up a little bit. So the 15% of it that gets to the wheels, where's it lost? Well, we talked about this. Some of it is lost to the friction with the road, so they call those tire losses. And eventually, if you have 30, 40,000 miles on your car, you have to get new tires because of that resistance. You have to get new brakes. And then air resistance is just the outside shape of the car just pushing against the wind. The faster you go, the worse this gets. So of the 15% that makes it to the wheels, that's the kinetic energy to drive the car down the road, 5% of it goes to fighting off wind resistance, 5% goes to frictional losses to the tires, and the last 5% is lost because if you start and stop a lot and you have to brake a lot, then all of that energy is lost. So your brakes get hot and you waste energy doing that. So if you're a very careful driver, this is something that you can brake less and get better gas mileage, okay? Just by not speeding up, slowing down, not always constantly hitting the brakes. You can do a better job. If you have a hybrid car that we'll talk about in a minute, then you can have regenerative braking, which when you press the brakes, it runs a small generators at the tires that extract some of that mechanical energy and make electricity that you can save for the to use in the car for later on. So Priuses and Teslas all have regenerative braking, which is really kind of cool. You also go through brakes a lot less. In a traditional car that doesn't have regenerative braking, or it's just complete waste, and you just go through brake pads and don't get any of the energy back. So again, pretty awful. 100% of the energy that's in the gasoline, only 15% gets you to driving down the road, and here's where it lost. This all has to go to zero because in the end, you don't do anything else positive except get to where you're going. Okay, a couple more. This is pretty cool. This is a comparison of fuel efficiencies of conventional hybrid and diesel vehicles. So here's some car companies that you know of. Too bad we don't have a Tesla on here, but you couldn't do miles per gallon because it doesn't use any gallons. You'd have to compare it from a different standard. But here's the conventional, is going to be this darker color here. Then here's the hybrid, and then here's the diesel. So Volkswagen offers all three. It offers a conventional, a hybrid, and a diesel. The hybrid gets the best gas mileage, okay, because it has a way to collect the energy that you're not using from the internal combustion engine, create electricity, and use it later on with a motor, and we'll talk about that in a second. Okay, here's a Mercedes. There's hardly any difference. This is a Mercedes E400 SUV. Between the hybrid and the conventional, you only get a little bit better gas mileage, which is crazy. Here's a Toyota RAV. You get quite a bit better. Ford Fusion, that's terrific. And then a Honda Civic. This is the hybrid versus the regular, 45 miles per gallon versus 35. And here's a Toyota Prius. The Toyota Prius only comes in a hybrid, so there's nothing to compare it to. But look, 50 miles a gallon. That's terrific. Okay, this is kind of cool. We'll just do the one on the left, right? So this is a one type of hybrid vehicle. It's called a parallel hybrid. So the energy in an electric, the energy in the engine and the electric motor for the Toyota Prius. The gasoline engine is at the left. The electric motor and generators are at the right. The engine is rated at 73 kilowatts, which is 98 horsepower. The motor, when you use the electric instead of it, is 60 kilowatts, which is 80 horsepower. And the diagram of Toyota hybrid synergy drive. So energy flows among the different components depend on the driving situation. All right, so this is the conventional internal combustion engine. You never plug this in. This is not a plug-in private, right? Plug-in would also have a little plug right here, where when you came home at night, you could recharge the batteries that way. So there really isn't any reason if you're going to get a hybrid, you might as well get a plug-in hybrid because electricity is a lot cheaper than gasoline. Okay, let's say you didn't plug it in though. Well, then the first thing you have to do is run it in a traditional format. If you run it in a traditional format, as the engine runs, the engine gets to this turbine, this power splitting device, some of it goes to the wheels to drive the car down the road, but some of it also goes to a generator that's constantly charging up a battery. So when you get to a light, there's a clutch in here that disengages the wheels because you get to a light, you're stopped, and instead of this spinning for no reason, now you're sitting at a light, all of the torque and all of the force to turn this wheel goes to this generator, so you're charging up while you're sitting at a light. Okay, now you have to hit the gas. Well, you have to hit the gas. Well, you need that power, so this is going to be less of it's going to go this way, or maybe none of it's going to go that way, and all of it is going to be going to driving you down the road. Okay? Let's say you're cruising along at a certain speed and your battery isn't very charged up. Well, it's perfectly legitimate to be some of it to go this way and some of it to go that way. Later on, half an hour later, the battery is completely charged up. The onboard computer recognizes that. Instead of going to the internal combustion engine, it shuts off the internal combustion engine and it uses an electric motor to drive the wheels directly. So this whole portion would be off. The last thing that they're not showing on here again was this idea of regenerative braking, where there would be regenerative braking at all four wheels. When you press the brake, instead of something physical like a drum closing up to slow you down, it would attach a generator to the wheel, and that generator would just naturally extract the energy from the wheel and slow the car down at the same time charging up the brake. So the regenerative part would come back to this generator here. Usually it's on all four wheels. And the coolest thing about it is you would go through a lot less brakes. As an emergency kind of stopping system, you wouldn't even notice it, but there is also disc brakes built in. But they would only go into place if you absolutely needed them. Most of the time you could come to a stop just using the regenerative braking. So very cool stuff. Okay, last thing. Here's a jet engine. Okay, so jet engine doesn't move up and down, right? And in 4 cycles, it's a continuous cycle. So what happens is you're still burning fuel. You're burning aviation fuel and oxygen, and the oxygen that comes into these chambers in here is first thing is compressed. So you have high pressure air meeting up with the fuel, and it is being ignited by a spark, and that or a continuous something to ignition system burns the fuel, creates the exhaust. The exhaust turns the turbines inside of here. The extra exhaust comes out of here, and this whole extra bypass air from that power from all of that burning and turning in a circle this time instead of an up and down motion, which a circle is much more efficient, right? It's almost reminiscent of the electric generation plant that I'll show you, where just the force of the combustion gas turns the wheels and gets the jet engine moving. Okay, so again, no up and down motion of a piston. A jet engine is a continuous process where the force of the gases from the combustion are just hitting little turbines and spinning them. So it's a spinning process instead of an up and down process, which is much more efficient. Up and down has a start and a stop at every section, and it's not very efficient at all. It's like very clinky. Okay, so jet engines are, we're able to generate much more power. And that kind of reminds me of this one, right? Where you think about it, here's the combustion of the food, the fuel and the oxygen under high pressure, and then it turns this turbine. Instead of generating electricity, you just generate so much air pressure that's going to push the airplane through the air. Okay, that's it. That's all of the important notes for Chapter 5. The only other video that I'm going to put up is I'm going to find a professionally made video on how an internal combustion engine works, and I'll post that one as well.